Hello. For our project for Mech 591, we chose to do the Scramjet design. And in this project, we have Matthew Lucio, Firass Elkaissi, and Zach Woodley. So what is a scramjet? A scramjet is a supersonic combustion ramjet. So airflow remains supersonic throughout the engine, and there's no rotating part, so it relies on the vehicle's speed to compress the air, which will then lead to the combustion and then the expansion, which will produce the thrust. Benefits. It's typically designed for flights at Mach 5 to 15. No onboard oxidizer is needed, and then a higher payload capacity and range due to better fuel efficiency. So the problem background. Basically, our objective was to find the optimal geometry of a scramjet engine flying at Mach 5 that maximizes performance metrics. So pressure recovery, thrust production. Assess is the assess the flow properties of the scramjet while varying free stream Mach and angle of attack. So for our analytical solution, we decided to use oblique shocks to relations to compute the shock angle for a given deflection. So the theta, beta, and M diagram formula. Find the pressure density and Mach number post-shock. Analytical prediction of flow properties after shock. Analytical predictions of flow properties at the nozzle. And then later compare with the simulated results to see how our analytical solution stood up to that. So for the sample cases, we decided for the input, we're going to use the free stream Mach number M1 equals 5.0, flow detection angle theta equals 10 degrees. Gas, we decided to use as a hydrogen and model it with gamma as a 1.4 as an ideal gas. And for the theta beta M relation, we use this equation, tan theta equals 2 cotangent, beta equals M1 squared, sine squared, beta minus 1 over M1 squared times gamma plus cosine 2 beta plus 2. And then we inputted it into this table and we got that beta equals to 19.37 degrees. We found the normal M1, which was M1.65. And for the post-shock properties, we were able to get this. So using the pressure ratio, we were able to get P2 over P1 equals 3.01. And then for the density ratios, we were able to get uh, this rho 2 over rho 1 equals 2.12. And then for the downstream Mach, we are able to get M2 equals 7.82. And then, so this is a G mesh that we created that we decided to make it unstructured, inspired by the X43A. So with this, we were able to export it as a SU2 file, and then make a configuration file. And then using Windows PowerShell, we were able to run that two simultaneously, which then led us to get a VTU file, which we then put into our peer review, which is later here for one of the SU2 simulations, one of the things we put and saw in peer review. And then later on for our SU2 results, modifying free stream Mach. So we decided to do it at 4.5, 5, 5.5, and 6. And we measured at the inlet and nozzle. So we had the Mach numbers for the theory and the simulated, the pressure in pascals for the theory and the simulated, and the density kilograms per meters cubed for the theory and the simulated. And you can see that there was some slight error so that they didn't match up perfectly with the theory and the simulated. But the thing that could account for that is the X43A is like a very like smooth surface, and we couldn't modify that exactly because we had a bunch of sharp lines, which could lead to like shocks and other mini shocks surrounding it. And then also we didn't have it so that I was like uniform throughout. So it wasn't a structured mess as well. It was unstructured. Because the geometry was so complicated, we decided to just go unstructured because we were trying to make it structured at first and it kept giving us errors. So we decided to go to an unstructured route. So yeah, so that could be one of the reasons why it wasn't exactly the same. And also because our simulated mesh and everything that we got was much more sophisticated than our theory, it took into account much more different factors that the theory did not, because it wasn't accounting for all the slightly different angles of like deflection due to all of the lines that we had. And then for the thrust per unit area, we got for the Mach 4.5, 5, 5.5, and 6. We did this by using like the mass flow. And for the theoretical thrust per unit area, we got for 4.5, negative 0.08. And the simulated was 2.99. Then for 5, it was negative 0.17 for the theoretical. For the simulated, it was 2.96. And then for 5.5, it was negative 0.26. And then for 3.92 for the simulated. And then for Mach 6, it was negative zero point 0.4. And then for the simulated, it was 4.69. So based on our simulation results, I would recommend a slightly higher Mach number of 5.5 and then 6. And then we decided that we were going to vary our angle of attack. So here are all the different angle of attack values that we did. We did 2, 4, and 6 because all of our original Mach values that we had in the previous slides were at a 0 angle of attack. So we calculated the Mach for the theory and the simulated, pressure for theory and simulated, and density for theory and the simulated. And then, therefore, after that, we were able to calculate that the theoretical angle of attack for the thrust per unit area, we got negative 0.22 at 2, and then simulated 3.09. For 4, negative 0.24 and 2.47, and negative 0.26 and 3.047. And yeah, that's what we were able to get. So overall, based on this, I would recommend an angle of attack of 6 or 2 at a Mach of either 5.5 or 6, so slightly higher than Mach 5 to get an optimal design for the scramjet engine. And yeah, that is it. Thank you so much for tuning in, and I appreciate all the work you did for having a great semester and being lenient overall with how like difficult everything was for a lot of the seniors this year. And I hope to stay in contact with you and the rest of the team does as well after graduation.